In section 1.7, we're going to talk about constructed functions. So in this section, we're going to talk about different ways to combine two functions to form a new one. So there will be 5 basic operations we're going to do here with functions. We could add 2 functions, we could subtract 2 functions, we could multiply 2 functions, divide 2 functions, and the 5th operation with functions, which might sound new, is function composition. And if you don't know what that is yet, we'll get into that, but that's when we're going to take one function and put it inside of the other function. Okay, so before we get into combining these functions, I want to run through some terms in business and economics that we will see come up a good bit in this course. So the total cost, let's say we have some business, is going to be everything I have to pay. So I'm going to have money coming in and money coming out. The cost is going to be everything that I pay. So there's 2 parts to the total cost. The first is the fixed costs. Okay, these are things that do not change. So these stay the same. Okay, so think about things like your rent. Your rent's not going to go up if you produce more of whatever you're making. These are salaries, things that are going to be constant, right? Then variable costs, right here, these are going to be things that vary based on how much you produce. All right, so these are going to change here. So let's say our business, we're making cheesecakes or something. Well, ingredients would be a variable cost because the more cheesecakes I make, the more ingredients I have to buy. Okay, so therefore our total cost is just going to be the sum of those things that don't change. So this is usually just going to be some number, right? It's not going to change. And then our variable costs, this is probably going to be where our input variable would go. All right, so for example, let's say my rent is $500 and then it costs me $5 per cheesecake. If I wanted to come up with a total cost function here, let's say my fixed cost would be the $500, which I have to pay no matter how much I produce, and then if my ingredients cost, I've already forgotten what I said, let's say $5 per cheesecake, that might be 5x. Alright, so that is total cost. Now our average cost would be if we take our total cost and then divide that by the number of items produced. Okay, so let's say our total cost, which we just found up here, was our fixed plus our variable, right? And then we divide that by how many items we produce, and we get the per item cost. So let's go back to the cheesecake example we just talked about. Let's say we produce 500 cheesecakes. All right, so my total cost here would be 500 plus 5 times, well, we produced 500 cheesecakes. Alright, so it costs me $3,000 to produce these 500 cheesecakes. Now let's say we want to find the average cost. Well, I'm going to take that $3,000 and then divide it by the 500 cheesecakes. So we'll call this A of x. Alright, so I'm going to take C of x, my total cost, and divide it by x, the number of things I produced. So this would be $3,000 over 500 cheesecakes, and we end up with $6 per cheesecake. So obviously if I'm going to sell these cheesecakes, I need to charge more than it's costing me to make each one. So I'd probably want to charge more than $6 per cheesecake. All right, now our revenue is going to be the selling price times the number of units sold. So this revenue here is just the money coming in. All right, revenue. I have not yet paid my bills. So my revenue, let's say, how much we're going to sell these cheesecakes for. Let's say we sell them for $10 per cheesecake. Okay, so my selling price then is $10 per cheesecake, and I'm going to multiply that by the number of units sold. Well, let's say we sold 500 cheesecakes. Alright, so then I would end up bringing in, my cheesecakes are going to cancel here, and we're going to bring in a total of $5,000. Now profit, this is different from revenue. This is what's left over after I've paid my bills. So this is what's left over after we have paid our bills. Okay, so profit is revenue. This is what the money coming in minus cost, what I need to pay out. So in the example of our cheesecakes here, we had revenue of $10 per cheesecake, and our cost here was $500 plus $5 per cheesecake. So just to refresh here, all right, we're going to call this one R of X. This is 10x, where x is the number of cheesecakes I'm producing. Then C of x, my total cost here, was 500 plus 5x. Okay, so what's left over, my profit, P of x, would be what I'm bringing in minus what I have to pay out. Alright, so what I'm bringing in is 10x minus my entire total cost here, which would be 500 plus 5x. Alright, now the break-even point is the point in which I have brought enough money in to cover my bills. Okay, so you can think of this two ways. The first way is to think, well, if I have sold nothing, do you see that we're always going to start in the red? Because I have to pay my bills, yet I haven't brought in any money. So at some point I sell enough that my revenue equals my cost. So one way to think of this is when revenue equals cost, I've brought in enough money to cover all my bills. Okay. Another way to think about this is when the profit equals 0. Okay, so my profit is going to start off negative, and at some point I've sold enough that I've paid that I can cover all my bills, and I'm now making money. So that, let's say this is, here we have number of units. Okay, so I'm going to start off with, and this is, let's say, P of x, my profit function. So I start off down here, I'm negative, and at some point I get out of the red, and then from there on out I'm making money. Okay, another way to think of this is with our revenue and cost functions. So let's say my revenue, I'm going to probably start here at 0, and let's say it's going to go up here, and we'll call this R of X. let's say my cost function looks something like this. So my revenue finally exceeds my cost, so I am making money. So that break-even point would be right here. Okay, so with those functions, those economics terms and I guess business terms in mind, if we were going to combine functions, well, we've already seen an example of subtraction here, right? This was revenue minus cost. And we've already seen an example of multiplication. This was maybe price times demand or number of units sold. And we've seen an example of division. You can think of this one as your average cost. So when we're thinking, we're trying to choose which operation to do here. We should pay attention to our units. To add or subtract functions, my input units must be the same. Okay, so it wouldn't make sense to add two functions if the input of one was dollars and the input of the other one was years. We can't add dollars and years. Okay, also the output units must be identical or the same. And again, we can't add degrees Fahrenheit plus cheesecakes. It must be the same. So my inputs, let's say both of my input units are time and both of my output units are money. When multiplying two functions, my input units must be the same. However, our output units must be compatible, meaning it makes sense to multiply these things. One thing that will help you when you're thinking about multiplication or division is to write out your units and see if things cancel. For example, when we think about price times demand, maybe my price is in dollars per unit or dollars per cheesecake. Okay, and then my demand, that's going to be how many units or how many cheesecakes I sell. Okay, and then hopefully you can see here that the units or the number of cheesecakes or whatever we're making are going to cancel out and we're left with dollars. So that's what I mean by compatible. It means it makes sense to multiply these two. Now function composition is going to be probably the operation that might be new to you, okay, but it's really easy to identify because what's coming out of one function is going into the other. So the output one function is going to be the same as the input of the other function. And these are going to be easy to identify because not only the notation, but also whatever's coming out of one function is going into the other one. All right, so let's look at an example here. The number of student tickets sold at a home basketball game is represented by S of W, where W is the winning percentage of the team. The number of non-student tickets sold is represented by N of W, 100 tickets, when the winning percentage is W. Okay, so we want to consider which of these 5 operations we might use. So the first thing we're going to do is think about our input units and our output units. Okay, so my input units for both my student function and my non-student function are W, which is the winning percentage. All right, so my input units are the same, so I can go ahead and eliminate function composition. So I'm now between addition, subtraction, multiplication, or division. Now when I look at my output units for my student functions, my units are tickets, right? And then my output units for my non-student function are 100 tickets. Okay, so now when I am thinking, are these units the same? Well, they're not quite the same, but they're close. They're both tickets, but one's in hundreds. So I'm leaning towards addition or subtraction, but let's think about, would these be compatible to multiply? All right, if I took tickets times 100 tickets, I would get tickets squared, which makes absolutely no sense. So I'm going to say the output units are not compatible here, so we're between addition or subtraction, but we're going to have to do a little bit of work to make those output units the same. All right, so in order to use function addition here, the output units must be the same. All right, so N of W is in hundreds of tickets. Well, to change this to just tickets, we're going to have to multiply this function by 100. So then my output units are just tickets. So my new function here for the total number of tickets sold is going to be the number of student tickets, S of W, plus the number of non-student tickets, but I multiplied this by 100 so that my units are now just tickets. So this gives the total number of tickets sold at a home basketball game when W is the winning percentage. So here, again, it made sense to add or subtract these two because what was going into both functions was the winning percentage, and with a little bit of work, what's coming out of both functions are going to be the number of tickets. So suppose more non-student tickets are sold than student tickets. We want a new function D that would give the number by which the non-student tickets was exceeded. So I'm guessing D here stands for the difference. So we have more non-student, so I'm going to take my non-student tickets here. All right, and then I'm going to subtract off the student tickets, and that would be by how many tickets are exceeded. And again, W is the winning percentage. So let's look at another example here. All right, so the sale of 12-ounce bottles of sparkling water can be modeled by D of X million bottles where the price is X dollars per bottle. Let's think back to what we've already seen about exponential functions. Here we have a B value that is between 0 and 1, so this is going to be decreasing, which makes sense. As I increase my price, as these bottles of water get more expensive, I'm going to sell fewer. People are going to say that's too expensive and not purchase them. Alright, so we want to come up with a function for our revenue. Price times demand. Right, or the price times the number of units sold. Okay, so we've got a function here for our demand, right? But what we need now is a function for price. Well, if we look, price is also the input value. So if you wanted to make this as simple as possible, you can think of P of X, the price, is just X. So my input units here for price is dollars per bottle. Okay, my output units for price, well, it's just going to be the same. It's just X. It's going to be dollars per bottle. Okay, my input units for my demand function are dollars per bottle. Okay, and then my output units for demand are million bottles. All right, so this is going to be million bottles. My input units are the same, so I know that this is not going to be function composition. So now I'm thinking of where I could add or subtract them. Well, I cannot add dollars per bottle and millions of bottles. Dollars plus millions of bottles makes no sense. Now I'm going to think, are these compatible? So if I took dollars per bottle and I'm multiplied that by million bottles, okay, yes, that does make sense here. Do you see my bottles are going to cancel out and we'd be left with $1 million? So we're going to lean towards function multiplication here. So we want a completely defined model for the revenue. So I'm going to call my revenue here R of X. Okay, so I know that this is going to be P of X, my price function, times D of X, my demand function. Okay, so my price function was just X. And then my units here, we just saw on the previous slide, my output units are going to be $1 million. Okay, so this gives the revenue in millions of dollars, where X here is the price, and my units there were dollars per bottle. And do we have a domain? I'm going to have to jump back over here. I guess our only restriction that we have is that the price needs to be positive. So we're going to say for X greater than or equal to 0. So if I wanted to find the revenue then using this new function when the price is $2.50 per bottle, this is an input, right? Because I'm given X, so this is an evaluate problem. Alright, so I have a couple options here. We've already come up with the equation here, so I can go to my graph menu and enter the entire equation just like I have it here. So X times 287.411 times 0.266 to the X. Alright, so I've got my entire revenue function in Y1, so I can go now jump back to my run menu and we want to evaluate that. Alright, so to get my Y1 I'm going to go to vars for variables. I want my graph variables, Y1, and I'm going to plug in that price of $2.50. Okay, so we get an output here of $26.221 million. Okay, now I realized that it was not hard to combine those two functions as we did algebraically right here, but there might be some functions that are a little more cumbersome, so I'm gonna, if you are following along in the note-taking guide, what some folks will do is put their price function in y1, their demand function in y2, and then go to y3 to combine the two. So here I'm going to go y1 times y2. I don't know that that is terribly efficient, but it'll get us there. So now I've got price in y1, demand in y2. I'm multiplying them, combining them in y3 using multiplication. So if I come back here, and now I want to evaluate y3, because that's where my revenue function is at 250, we get the same answer. So I imagine most of you guys will use the first strategy. So in example 3 here, we have one function for the contamination level of a lake, which is just the square root of P. Okay, and so our units for contamination are parts per million when the population is P people. So I'm going to input the population and the output is the contamination. Okay, the population of this community can be modeled by this second function where my input is the number of years since 2000. Okay, when I'm considering which operation here, one thing that's going to help me jump to function composition fairly quickly is the notation here. Do you see my output notation here, P, which is the population, is the same as my input notation here, P? That's one thing that would lead me towards function composition. But let's look at our units here. So our first function, f of p, my input is the population in people. Yeah, so my input units here are people. Okay, and then my output units here are parts per million. Okay, for my second function we have over here, the input units are the number of years, and then the output units are the population measured in people. Okay, so because what's coming out of this function, people, so what's coming out of this function is people, which is going into my second function, lets me know that we're going to use function composition here. So why would we compose these two functions? Because the output of P of t, which is people, is the input of f of p. So what's coming out of one function is going in the other function. So here in my first function, we're inputting t, which is the number of years, and then we're applying p of t, which gives out the population, which is measured in people. Okay, then we're inputting that into f of p, and we're getting out the contamination. And our units for contamination here are parts per million. Okay, so if we were going to combine these algebraically, I want this new function, which we're going to call f of t, because we're going to bypass the population here. So I'm going to take the square root of this whole function that we now have for the population. What I'm doing here is I'm taking this entire function for the population and I'm going to plug it into my contamination function. So that would be 400 t squared plus 2500. Okay, so my output units here are parts per million. So this gives the contamination. Alright, and my units here are in parts per million. And my input now, I have completely eliminated the population. My input variable is now t, so that is where t is the number of years since 2000. And let's flip back here and see if we were given a domain here. So t is the number of years since 2000. We do not have a domain here, so we are going to say our domain, let's go from 2000 to, it is currently 2016, so let's go 0 to 16. Alright, now we want to calculate the level of contamination in 2007. So again, this would be an input value. So this would be an input value of t equals 7. Okay, so there are a number of ways to do this. Okay, we have already algebraically composed our function here, and we have our function f of t, which is the square root of 400 t squared plus 2500. Okay, so one way to do this, probably the most straightforward, is I'm going to take 7 and plug it in for t. Okay, another way to think about this is I could do this in 2 steps. I would take p of t, which would be 400 t squared plus 25. I could plug in 7 here for t, and I would get out the population. Then I could take whatever this number is here for the population and plug it in to f of p. So I would take my answer here and plug it in. Alright, so let's look at trying this both ways. We'll start with the way that I think is the most straightforward, which, since we have already composed our function, I can just put my entire composed function into y1. Make sure you open parentheses for the beginning of your radical, 400x squared plus 2500, and then close the parentheses for the end of your radical. Then, because this is an evaluate problem, I just want to plug in 7 into my composed function. and we get an output value here of 148.661 parts per million. Okay, our second strategy, which I think might be a little cumbersome, is I could put one of my first function here in y1, which would be my function for the population. So this is 400 x squared plus 2500. Then in y2, I'm going to put my second function, which is the square root of the population, and then in y3, I'm going to compose them. Now, I have to think about which function is going to go on the outside. Well, that's going to be my contamination function, which I have in y2 and I'm going to plug into that my population function, which is y1. So then if we go back to our run menu, if I now evaluate my composed function, which is in y3, at 7, we get the same answer.